Good morning, my fellow scientists. It is Wednesday, October 11th, 2017, and I'm going to go through the results of the silver-plated all-iron cell today. I'm afraid they're not as good as one might hope, but let's go through how it was constructed and how it performed. First, I took silver foil, silver leaf really, and applied it to this plastic coating. Then I put that into the cell with a iron anode in a little Nafion impregnated paper packet. That then goes against a paper spacer, which then goes against the carbon sponge that holds all of the catholyte, silver current collector, all goes in a plastic bag, and we add iron EDTA. When all that is assembled, we can cycle the battery up and down, charging and discharging. You can see the charge-discharge curves here. There's clearly some interesting chemistry happening as it charges up. It hits 400 millivolts, and there's a plateau indicating that there's a chemical reaction happening, and then we get a second plateau higher. That may be just conductivity, and you can tell that there's some non-productive charging going on there, because when we look at the charge versus discharge per iteration, that is to say how much electrons was transferred during the charging and how many electrons were transferred during the discharge, there's a clear difference. That indicates that essentially a lot of the work I did to charge the battery was just going into stirring electrons around instead of going to a chemical reaction. So clearly I overcharged it, that's fine. It discharged to the same amount every time, and you can see that the discharge was somewhat stable. But when I was done with all that, I looked at the silver plate on the back and discovered that it's actually somewhat degraded. So you can see this is what's left. And yeah, it's no longer a contiguous surface by any means. I don't know if that, there we go. You can see pretty clearly that most of the silver has been removed from that plastic. So evidently the anodic reaction is pretty aggressive, maybe in combination with the EDTA. A low level of dissociation of the silver is just irreversible, and it goes up and gets chelated and dissolved. So that's no good. That also led me to think maybe the gold was also doing the same thing, that was actually pure gold. Per the suggestion of a commenter, I applied a little bit of nitric acid to the gold leaf, or the supposedly gold leaf, that I suspected wasn't gold leaf at all. And initially there didn't seem to be a whole lot of reactivity. Got me thinking maybe this was more pure than I had originally thought based on electrochemistry, but after 5 to 10 minutes I came back and discovered that in fact it was dissolving and falling apart in that nitric acid. So yeah, not pure gold. So the next step is to adjust the chemistry so that etching doesn't happen anymore. I'm going to try, as I mentioned yesterday, I'm going to try to use iron hexacyanide instead of iron EDTA. Should have faster electron transfer. It may inhibit the dissociation of the metal current collector, but the metal current collector does seem to be making a difference, at least before it dissolves, because the carbon by itself just has a very high resistance and makes it difficult to run the battery. So if you like hearing about battery development and all the successes and the failures that come with it, tune in Monday through Friday. We talk about iron and batteries and chemistry and results right here in the Allen Lab.